So yeah, thank you for having me. And so my name is Giuseppe di Pasquale, and yeah, I'll present my last year progress with my thesis, multidisciplinary optimization of space mobility maneuvers for commercial applications of micropropulsion. So my supervisors are Manuel Sancur-Corivo from UC3M and Daniel Perez Grande from UNA Space. So this is as Borja, an industrial PhD, collaboration between UC3M and UNA Space. So this is the content of my presentation. I will do a brief introduction of the thesis fundamentally, and then cover the 4 contributions that are fully included in my thesis. And finally, some conclusions, some closing remarks, obviously discussing a bit about the publications and my contributions. So a brief overview on the motivation of my thesis. Fundamentally, I believe everyone has heard about the new space economy. So this privatization of space, we have all these industrial players, SpaceX, the lowering of the cost of launching. And one of the great consequences here is also the adoption of these small satellites. We can see here, the surge of these nano satellites. The trend is kind of exponential, but I believe this was shown by Borja as well, but we also have a problem here, which is the very low adoption of propulsion, in general, of mobility solutions. Now, this is a problem because fundamentally space mobility, so in general, ways to move in space, to change your orbit or to maintain it, are very important because you can increase your lifetime of your mission, you can deal with sustainability. So sustainability now, it's a very big important problem here because we have the debris, so we want to be able to do collision avoidance maneuvers, we want to be able to do the orbiting, so the commissioning of the satellites. So obviously this is a problem, the fact that nanosatellites have this very low adoption, below 10%. The reasons behind this are related to the technology, so it's very hard to include propulsion technologies that fit in these very tight constraints of the propulsion system, but also the fact that the problems of selecting the propulsion, the right system is a very highly multidisciplinary problem. So it's very complex. You have a lot of things that you need to consider, and it's very critical also to do so at early stages, because all the choices you make at an early stage are a commitment to the cost in the subsequent phases of your project. So it's very clear, it's very critical to be able to explore these things at an early stage of the mission. So in terms of thesis objective, fundamentally the overarching objective is the development of a framework for the multidisciplinary optimization of commercially relevant applications. And obviously, I mean, small satellites operating in LEO constellations, in the LEO environment. And also another big topic here is constellations. We have this emergence of these mega constellation concepts, and obviously mobility solutions for that specific application are critical, and obviously a very great opportunity for commercial players. So in particular then exploring some specific applications for this framework, or let's say solving methodology for this problem related to concurrent engineering. So modeling, fundamentally solving the problem of selecting the maneuvers at the same time with the propulsion system and associated or coupled subsystems. Also exploring the modular propulsion system design, which is something very tied to the company UNA Space philosophy or approach to the market with the modular propulsion system Athena that I believe Borja mentioned before. And then some other things to explore, which are, for example, variable performance transfer optimization, which is a topic in which fundamentally you exploit in a better way the propulsion technologies that exist right now, which is a topic that in literature is not that much explored. And finally, obviously, some objectives related to the optimization of the deployment of constellations, which, as I mentioned before, is a very commercial relevant application. So just a brief overview on the problem. So as I mentioned before, this is selecting the right propulsion technology for your mission is a highly multidisciplinary problem because you have large coupling between the various disciplines. So here, for example, you see the trajectory, the propulsion, the power system, and the ADCS. These are some variables that couple, let's say, the problem in a way. So if you don't consider this at an early stage, you maybe will overlook some fundamental aspects of the mission that will probably mean that you will have to rework, or the system that you select early on will not fulfill some specific constraints of the mission. So yeah, we need to adopt some multidisciplinary optimization techniques, something that can deal with all this complexity and all these coupling variables. Additionally, the problem can have hybrid variables, so we can have discrete variables because we want to be able to select, for example, the system, a component, a specific component, but we also have continuous variables. For example, if we're selecting the propulsion system set points or specific continuous parameters. And at the same time, we want to focus on multi-objective problems because, as I mentioned before, we want to apply this methodology at early stages. And having the possibility of exploring multiple objectives is very critical. And additionally, we want to be able to explore different alternative objective functions which are related to the system level optimization, not merely the trajectory optimization, which is what you will find usually in low trust optimization research. So this is a bit the framework in a nutshell. In principle, in this framework, we're modeling all the subsystems and their dynamics. So we have the dynamics of the, obviously, orbital dynamics, but also models for propulsion, for the power system, the ADCS, and so on. All the highly coupled system that I mentioned before. And we're solving the trajectory optimization using a predefined control law. Now, here you have the equations, basically, that we're using. The idea here is a bit different than classical methods, for example, direct and indirect methods for solving the trajectory optimization problem, because this is much more robust. So it's more related to the commerciability of the tool, fundamentally. All of this is wrapped in a genetic algorithm, fundamentally, that is capable of tuning the parameters of these predefined control laws, but at the same time making decision on the system at system level. So defining variables for the propulsion system, for the battery, or selecting a specific system. So what you would typically get as a solution of applying this framework to a given mission is this kind of Pareto front. So as I mentioned before, we have multiple objectives. In this case, we have the payload fraction. So as you can see, it's not a classical objective that you would have maybe in pure discipline-based trajectory optimization, but it's more related to the choices that you make on the system, so that they affect the whole system. And in this case, we were exploring a certain maneuver, and we have each of these points is a different solution. So it's a different propulsion system that is able of fulfilling that maneuver, and it does so in a different way, because as you can see here, we have the deployment time. So if you have basically a very beefy system with a lot of thrust, you will do the maneuver faster, which is kind of intuitive. Otherwise, if you want to save mass, you will have a smaller system with less thrust in this case, but it will take more time to do the maneuver. Another aspect investigated was this more concurrent approach to the design of the system. So we are including here as well the EPS, so the electrical power system. And as you can see now, the Pareto front is improved. So we have non-dominated solutions compared to the previous case, simply by exploring the problem from a higher, from more high point of view, let's say, from a higher perspective. So we also have more complex families of solutions. In particular here, I'm highlighting the impact of the configuration of the solar panels, basically. So yeah. Moving on to the next contribution, which is related to variable performance transfer optimization. So here the idea, as I mentioned before, is to exploit the technological advantage, the technological hedge that these electric propulsion technologies offer. So the fact that we can modulate the thrust over time as we do the maneuver. And the idea here, the methodology, basically, it exploits this parameter, which is called maneuvering efficiency, which is basically a way to quantify within the orbit how efficient it is to actually thrust. And the idea basically is that of tying this maneuvering efficiency through a parametric curve to the performance of the system. So this way we can modulate the set point of the propulsion system throughout the maneuver, and it's tied to this maneuvering efficiency. Obviously, it means that there is a big impact on the specific propulsion technology that you're using. So some results. The blue curve is for a constant ISP, so a maneuver. We're doing a certain maneuver with a constant ISP. So if we apply the methodology, as you can see, we have the red and the black curves. They basically represent these variable performance maneuvers. And as you can see, we are obtaining improved results, especially in this region, and particularly these points that I have highlighted, and specifically S1, we have about 18% of improvement in both objectives, which, considering that you're just adding a small complexity increase, so modulating the thrust as you proceed in the maneuver, it's a good advantage, I would say. This also gives a bit of an overview of these points. For example, you can see here how the ISP varies throughout the maneuver, thanks to the methodology and how it changes in the various cases. So, for example, in this one, we're going more towards the high end of this specific case. And finally, the thing I mentioned before, so this is highly dependent on the technology. So some technologies will benefit less or more, depending on their performance models, that we can include these realistic models in the methodology fundamentally. Then moving on into the constellation, the big topic of constellation, we have principally explored the optimization of constellation deployment using electric propulsion.
You need to pass a bit. You have already consumed the 10 minutes.
All right.
Finalize.
Perfect, perfect. So I will go quickly in this one because so I can probably mention the new stuff. In this one? Okay. So in this one, basically, we're exploring strategies to deploy satellites in space using electric propulsion and exploiting the G2 perturbation, and basically analyzing these two methods, which are a parallel and sequential method. Some highlights: in principle, there is a trade-off between the two methods, which depends on the injection altitude, which prompted one of the new articles that I worked on in the previous year, which is basically the exploration of the full space mobility problem. So starting from the surface of the Earth and going to the slots of the constellation. In principle, including the launcher selection into the problem. We're expanding the multidisciplinary problem also to cover the aspect of launch and therefore including some logistical constraints, for example, manufacturing rate and this kind of aspects of the mission. So this led to a modification of the architecture in which we included the launcher selection discipline solved with a mixed integer programming, and the maneuvering strategy, which is a modification of the previous paper using a semi-analytical formulation, which makes it much more performant. Just to give you some results on this, this is the kind of Pareto form that you get. So the cost of the total launch, so considering all the launchers' cost, and the duration of the deployment of the full constellation, which obviously depends strongly on the launcher that you select. You can see here there were three kinds of launchers here, but also on the strategy that you're adopting. So the maneuvering that you're doing in orbit. So just very quickly some details. For example, the fastest solution was performed with selecting all the smallest launch vehicle, but there was it's a very rapid cadence, but it's more expensive. Whereas the slowest solution, but also the cheapest, was performed with very big launchers, launching a lot of satellites, but then performing these very large maneuvers to deploy them in space. So this is the kind of solutions that you get from this methodology. So just to wrap it up, mentioning some of the publications. The new ones are this one that's conference proceeding from UCAS, another couple of papers still from UCAS of last year, the publishing of this new journal paper on variable specific impulse maneuvers optimization, publishing now an Acta Astronautica Method journal paper on the topic of launcher selection that I just mentioned. And finally, a colleague of mine will present another paper related more to the attitude side of the problem. The presentations, the new ones is just the UCAS, again, last year, nothing new on this side. And finally, some other activities, participation to several workshops, to various seminars, presentation at Semana de la Ciencia, and supervising some master and bachelor thesis. And so, yeah, that's it. Thank you for your attention. If you have any question, happy to take them.